Hello, lovely humans. Today we're going to keep talking about area of regular polygons, but with slightly more complex problems. So problems where we have to use properties either of specially right triangles. So those are 45, 45, 90 triangles, or 30, 60, 90 triangles, or problems where we have to use trig. So our basic trig functions of sine, cosine, and tangent. Okay, so before we do that, I want to talk a little bit more about figuring out angles, because I think in the previous video I wasn't super clear, and I want to make sure we all are talking about the same thing. Okay, so this hexagon I've split up by drawing all 6 radii. And when I do that, you can see that I have 6 triangles. All of these triangles are congruent, which I hope you can see given that this is a regular triangle. And they're also all isosceles triangles, which we know because all of the radii are congruent. So we know these are isosceles triangles. Okay, and so we're going to use those pieces, those 2 facts, to figure out what some of our angles are. So the first thing I'm going to talk about is the central angles. And so the central angles are each of these angles right here that are made up of the radii in the center. Okay, and all of those central angles are going to be congruent because these are congruent triangles. And so the way we find one is we know that a complete circle is 360 degrees. Yes? So we're going to take that 360 degrees and we're going to divide it by the number of central angles we have, which is 6, since they're all congruent. And so in this case, we know a central angle here is going to be 60 degrees. Okay? So then something that often happens is we draw the apothem. Well, something that always happens is we draw the apothem, because in order to find the area, we need to know the apothem. And so then often we're asked to then find this angle right here. And that angle, so the apothem, remember, bisects the opposite side. And we know that if we have a perpendicular bisector of an isosceles triangle, so once again, we know these are congruent. We know we have an isosceles triangle. The apothem in green is a perpendicular bisector. We know that it is also an angle bisector. So we know these 2 angles are congruent. And since we know those 2 angles are congruent, we know that this angle right here is 30 degrees. So the apothem is always going to bisect the central angles. Now I also want to talk about the interior angles. Okay, so that would be that angle right there, this angle right here, etc. So the angles that are formed by the actual hexagon, regardless of the radii that we draw. Okay, and we know previously from the polygon angle sum theorem that to find the sum of all of the interior angles, we use n minus 2 times 180. And then to find the measure of one angle of a regular polygon, we'll take the sum and we'll divide it by the number of sides, or the number of angles, since they'll be the same. So for this hexagon, we would do 6 minus 2 times 180 divided by 6. And that would give us the measure of one interior angle. And so when we do that, we find that that is 120. So this green angle right here is 120 degrees. Now, I am running out of colors here. Once again, often we want something different. Generally, we're asked, okay, I want just this angle. And so just like the apothem bisects the central angles, the radii bisect the interior angles. And so this angle right here is going to be 60 degrees. Or I could say, with my drawn apothem, this angle right here is 60 degrees. Okay, so those two attributes are going to be used a lot. You're going to be asked to find half of the central angle or half of the interior angle a lot, because we want to use these right triangles. We can do a lot of things with right triangles, and we need the apothem, which creates right triangles. So it's really important that you understand how to find all of those angles. So let's look at this actual shape and now do what we've been asked to do with the area. So we've been asked to find the area of this hexagon, and we know that the side length is 3 millimeters, okay? So let's mark that, 3 millimeters. All right. So I'm going to redraw this triangle down here, because that's going to be your best strategy. Just redraw the triangle. Most of the time it's hard to draw the polygon anyway, and the triangle is really the only part we care about. We don't care about the rest. Okay, so I'm going to redraw that isosceles triangle formed by my two radii. I'm going to redraw my apothem, because that's important. And then I know the entire side is 3 millimeters, which means half of it right here is going to be 1.5. And I've already figured out my angles. I know that this angle at the top is 30 degrees and this angle at the bottom is 60 degrees. So I have a 30, 60, 90 right triangle. And the 1.5 is my short leg. So I always know that the short leg, we could call that S. I know that my hypotenuse is 2S, and I know that my long leg, which in this case is my apothem, is S root 3. So that means in this case, the length of my apothem is going to be 1.5 root 3. Okay, because it's whatever the short leg is times root 3. So now that I know that apothem, I can start using my area formula. So area, as a reminder, is 1/2 the apothem times the perimeter. So that will be 1/2 1.5 root 3 times, and then my perimeter, well, I know one side is 3, and there are 6 sides total, so I'll just say 3 times 6, or I could just, since I can do that in my head, I can just write 18. So I know the perimeter is 18 because it's 3 times 6. So now I'm going to leave this in simplest radical form. If you use special right triangles, so if you have a 30, 60, 90 triangle or a 45, 45, 90 triangle, you should always use special right triangles, and you should always leave your answer in simplest radical form. So what that means in this case is we're going to do 1/2 times 1.5 times 18, and that will give us 13.5 root 3 millimeters squared. And there's our answer using special right triangles. So let's look at our next, or our last example. And this says the radius of a regular octagon. So we don't have a picture this time. I'm not going to ask you to draw a regular octagon. I'm not going to draw a regular octagon because honestly, I can't. So as I said earlier, all we really care about are those triangles that are created by the radii. So I'm going to draw one of my isosceles triangles that's created by the radii. Okay? And it says the radius is 5 centimeters. So I know that this right here is 5 centimeters. I'm going to use that to help me. So I'm going to draw my apothem. And I know that I need to figure out my angles. Okay? So actually, I'm going to undraw my apothem. I'm going to figure out my angles first, and then I'll deal with the apothem. So I know that all of the central angles together make a circle, and so it's 360. So I'm going to divide that by the number of central angles, which is 8, since it's an octagon. And 360 divided by 8 is 45. So this angle right here is 45 degrees, okay? So then when I draw my apothem, this new angle for my right triangle is going to be 22.5 degrees. All right, I can go and find this bottom angle right here, but I actually don't need to. This isn't a 30-60-90 or a 45-45-90, so I know I'm not going to use special right triangles, and I am going to use trig. Okay, so I've got a 22.5 degree angle. I want to know my apothem that's right here, and I want to know the length of my other side so that I can find the perimeter. So I'm going to call that x. Okay, so now we're going to use trigonometry. I'll start with finding the apothem. So the apothem is the adjacent side to my 22.5 degree angle that I have. And since I have the adjacent, and then I know this is my hypotenuse, that's also 5 centimeters because all the radii are the same. I'm going to use cosine. So I'll have cosine of 22.5 equals, and then the adjacent side is A, my apothem, and the hypotenuse is 5 centimeters. So I'll multiply both sides by 5 to solve, and I'll find that A is approximately 5 cosine 22.5, 4.62. Okay? So we found A. Now we need to find x, or our opposite side. And that's going to be sine, because x is opposite of our angle. So now this will be very similar. Sine of 22.5 is equal to x over 5. X is the opposite side. 5 is the hypotenuse. I'll multiply both sides by 5 to solve for x. And I'll get x is approximately 5 times the sine, 5 times the sine of 22.5 is going to give me about 1.91. Okay, now, it's important to remember that 1.91 is just half of the side. It's not the entire side. So we are going to have to double that. So let's talk about finding our area. So area is, again, 1/2 the apothem times the perimeter. So in this case, it's going to be 1/2 times our apothem, which is 4.62, times our perimeter. So our perimeter is going to be a side length, which is 1.91 times 2, which is 3.82. 3.82 times the number of sides, which is 8, because it's an octagon. So then I just plug that into a calculator. 1/2 times 4.62 times 3.82 times 8. And I'm going to get about 70.59 centimeters squared. Ooh. I did not give very much space right here to write that. So if you have bigger handwriting, that might be kind of hard, but do your best. Okay, so the important parts is finding the angles. Be really careful with finding the angles. Remember that the central angles are 360 divided by the number of sides, which is the number of angles. And to find the interior angles, we use our interior angle formula from our previous unit. Okay, and then you can either use special right triangles if you have 45-45-90 or 30-60-90, or you can use trigonometry if you have angles besides those special right triangles.